Good evening, everyone. So in the previous lecture, we discussed about the Amperes circuital law. In this lecture, we'll be applying the Amperes circuital law to calculate the magnetic field due to different systems, right? So we'll be applying the Amperes circuital law to calculate the magnetic field due to different systems. So here you can see in this picture, we have a thick wire, right? We have to calculate a magnetic field due to thick wire. In the last lecture, we calculated the magnetic field due to thin wire as well, right? But if the wire is thick, then how we can calculate the magnetic field outside the wire and how the magnetic field is going to vary inside the wire as well, right? So there will be a variation between the magnetic field outside the wire and the magnetic field inside the wire. So let's try to calculate how we can actually approach this to find the magnetic field in both the regions, right? So we can see here in this diagram, let's suppose this is a wire, right? This is a wire. And the current flowing through this wire is I, right? I current is flowing through this wire, right? So I is the current flowing through this wire, right? This is the total current I flowing through the cross section of wire, right? And if we are to calculate the magnetic field just outside this wire, what we will do is that we'll just draw an Amperean loop just outside this wire, right? With the common center, right? Let's suppose this is the Amperean loop outside this wire, right? So we can draw the Amperean loop outside this wire, right? At a distance of r from the center. So it means that this will be the distance. This will be the distance r from the center. This will be the distance r from the center to this point of Amperean loop, right? So Amperean loop here is a circular loop, right? And we know that at each and every point on the Amperean loop, the magnetic field will be a constant in magnitude, right? But it may have different directions at different points on the Amperean loop, right? So we can use this Ampere's circuital law, and let's apply this Ampere's circuital law on this Amperean loop, right? For the region outside, So integral of B dot dl will be equal to mu naught times the current enclosed, right? Mu naught times the current enclosed. When the Amperean loop is outside this wire, then the total current enclosed will be the current I flowing through this wire, right? So I enclosed will be the total current I. So I enclosed will be equal to I, right? So if I enclosed is equal to I, right? So integral of B dot dl will be, it will be integral of B dl, because the angle between magnetic field vector and the dl vector of this Amperean loop will be equal to 0, right? Because due to a wire, the magnetic field lines are circular in nature, right? So it will be B dl, right? That will be equal to mu naught I. So B is a constant, right, on the circumference of a loop, right? So we'll just take it outside the integral. We'll be left with integral of dl, right? That will be equal to mu naught I. And dl is nothing, it's the total length or the total circumference of this Amperean loop, right? Integral of dl will give us the total circumference of this Amperean loop. So this will be equal to 2 pi r, right? That will be equal to 2 pi r. That will be equal to mu naught I. Or we can say magnetic field outside this Amperean loop, outside this current carrying wire will be equal to mu naught I upon 2 pi r. So this will be the magnetic field outside this current carrying wire. This is a thick wire. Since the total current enclosed by this Amperean loop was the current I, so the magnetic field is mu naught I upon 2 pi r, right? But the thing is that how the magnetic field is going to change inside the wire, right? Inside the wire, when we draw an Amperean loop at some distance r inside the wire, then the current enclosed by that loop will not be the same current I, right? Will not be the same current I. Then we use the concept of the current density, right? We use the concept of current density, right? So current density J is equal to I upon A, right? I upon A. And it's a constant for this thick wire, right? Current density here is a constant, so it will be I upon 2 pi capital R, where capital R is the radius of this capital R is the radius of this thick wire, right? This is the radius of this thick wire. So if we have to calculate the current enclosed by the Amperian loop inside the wire, then the current enclosed will be equal to, we'll be using the concept of this current density, that will be equal to I upon 2 pi r, right? 2 pi capital R multiplied by the sorry, it will be pi r square, not 2 pi r. It's not circumference, it's area, right? So it will be pi r square here, right? I upon pi r square, right? So it will be pi r square here, right? Pi capital R square. And multiplied by the area enclosed by that Amperian loop inside the thick wire. That will be pi small r square, right? Pi small r square. This pi and pi will get cancelled. We'll get I enclosed as inside the Amperian loop, which is inside this thick wire. That will be I times r square upon capital R square, right? So this will be the current enclosed by the Amperian loop, which is inside this thick wire, right? Inside this thick wire. Let's suppose this is the Amperian loop, right? I will write it as AL. So this is the current enclosed by this Amperian loop, which is inside this thick wire, right? So once again, we'll be applying the same concept, same what we call as Ampere's circuital law. That's line integral of magnetic field, right? Integral of B dot dl. That will be mu naught times I enclosed, and the I enclosed is IR square upon capital R square, right? So this will be the current enclosed, correct? And the integral of B dot dl will be nothing. It will be B times dl. Integral of dl will be equal to 2 pi small r, right? 2 pi small r. That will be equal to mu naught IR square upon capital R square, right? Upon capital R square, right? Upon capital R square. So from here, R and R will actually get cancelled. So we'll be left with P is equal to mu naught I times R upon 2 pi R square, right? 2 pi R square. So you can see here from here that magnetic field is now directly proportional to the radius R, right? Magnetic field is directly proportional to the radius R for inside, right? For inside region, the magnetic field is directly proportional to the radius R. And for the outside region, the magnetic field is actually inversely proportional to the radius R. So you can see in this diagram that suppose this is a thick wire, right? This is a thick wire. At the center of this thick wire, the magnetic field is actually zero, right? And magnetic field is then directly proportional to R inside this thick wire. So it will be a straight line up to the surface. Up to the surface, it will be a straight line. Or we can say that the maximum magnetic field will be at the surface of this thick wire. At the surface of this thick wire, the magnetic field intensity will be actually maximum. And then it will be decreasing as a function of R, that will be inversely proportional to R, right? So this will be the magnetic field for outside region, and this will be the magnetic field for inside region. For inside region, magnetic field is directly proportional to R, and for outside region, the magnetic field is inversely proportional to R. So this is the behavior of the magnetic field due to thick wire, right? Now, same goes with the slender as well, right? You can see here we have slender. We have a slender. Now we want to calculate the magnetic field due to this slender carrying current I through its area of cross section. It's a hollow slender, right? Hollow slender. The current I is flowing through it. The outer radius of the cylinder is given as P and the inner radius of the cylinder is given as A, right? The current is I. We have to find the magnetic field in both the regions, outside the cylinder as well as inside the cylinder, right? So what we'll be doing is that we'll be once again applying the Ampere's circuital law, right? For outside the region, this will be the Amperian loop, right? This will be the Amperian loop. So this will be the Amperian loop for outside the region, right? So we can just redraw it. So somewhat like this will be the Amperian loop for the outside the region, right? So this will be the Amperian loop for outside, right? For outside. For outside region, this will be the Amperian loop, right? For outside region, this has to be the Amperian loop. Correct? So we'll be applying the same what we call as by Ampere's circuital law to calculate the magnetic field for this cylinder as well. So it will be integral of B dot dl for outside region, right? That will be equal to mu times mu naught times I enclosed, and I enclosed here is total current I, right? So once again it will be B times 2 pi r, where small r is the radius of that Ampere loop. So it will be mu naught times I. The magnetic field will be actually equal to mu naught times I upon 2 pi r, right? So this will be the magnetic field due to this cylinder, right? Outside this region, right? Now the question is that what will be the magnetic field due to this hollow cylinder inside this cylinder, right? There will be two regions. One region will be a hollow region, another will be a region which will contain some current, right? Which will contain some current. In this hollow region, if we try to calculate the magnetic field in this hollow region, and if we draw an Amperian loop in this hollow region, but this Amperian loop will not actually this Amperian loop will not enclose any current, right? So the magnetic field inside this Amperian loop will be actually equal to zero, right? So this equation is valid for r greater than b. It means it's for the region which is outside the cylinder, right? R greater than b, the magnetic field is actually mu naught I upon 2 pi r, right? And similarly the case second will be for the region r less than a, right? For the region r less than a, there will be no current enclosed, right? I enclosed will be equal to zero, or we can say the magnetic field in the region where in the region r less than a equal to zero, right? Because the current enclosed is zero, right? So there will be no magnetic field in this hollow region for this cylinder, right? Similarly, if we have to calculate the magnetic field, right? If we have to calculate the magnetic field in the region, if you want to calculate the magnetic field in the region greater than r greater than a, right? But less than b, right? R greater than a, but less than b, right? So in the region r greater than a, but less than b, we have to calculate the magnetic field. Now, once again, we'll just draw an Amperian loop in this region, right? And use the concept of the current density once again. So if we use the concept of the current density in this region, right, we know that current density is nothing that will be equal to J upon for the total current, that will be J is equal to I upon pi times B square, right? Pi times B square, correct? Now we have to find the current enclosed in this region, right? In this region for R greater than A, less than B. So the current enclosed in this region will be given by I enclosed, right? I enclosed. So it will be actually I upon pi b square, multiplied by the, if we draw Amperian loop in this region, right? This is the region where we have to draw an Amperian loop, right? This is the region. This is the region where we are actually drawing an Amperian loop, right? So this is the region, right? So in this region, let's suppose the radius of this Amperian loop is a, right? R, radius of this Amperian loop is equal to R, right? Now we have to find the current. So the current density is I upon pi b square. Then the current enclosed in this region will be actually, it will be pi times R square minus pi times A square, right? So that will be the current enclosed in this region. Or we can write, it will be I times R square minus A square upon B square, right? Upon B square. So this will be the current enclosed in this region, right? This will be the current enclosed in this region. If this is the current enclosed in this region, then magnetic field B will be, so we'll be using the same circuital law, right? That's P dot dl. That will be equal to mu naught times current enclosed. That's I upon B square multiplied by the R square minus A square, right? So this will be the current enclosed, right? So the magnetic field will be nothing. B will be equal to mu naught I times upon B square, and the integral of dl will be 2 pi r. We'll just write here 2 pi r, right, multiplied by the factor r square minus a square. So this will be the final magnetic field, or we can rewrite it as mu naught I times r square minus a square upon 2 pi r b square, right? This will be the magnetic field in this region, right? So this will be the final magnetic field in this region or inside region of this hollow cylinder. For r less than a, the magnetic field will be 0. And for r greater than b, the magnetic field will be inversely proportional to r. And for the region r greater than a but less than b, so this is the magnetic field, how the magnetic field is going to vary in this region, right? Now, there's a question. This cylinder is not actually a hollow. This cylinder is not actually a hollow cylinder. This is a. Let's suppose that this is a what we call as solid cylinder, right? Then for solid cylinder, then this A will actually tend to 0, right? For solid cylinder, right? So we can actually apply this equation for solid cylinder as well, right? But we can substitute the value of A in that case equal to 0, because then it will be a complete cylinder, right? Then it will be a complete cylinder, and the magnetic field will then exist inside region as well, right? So there will be no non-zero magnetic field inside this region. So magnetic field will be 0 only. In that case, the magnetic field will be 0 only. In this case, we have a hollow cylinder, right? And there is a hollow region, and the current enclosed is actually 0, right? So we can actually apply this equation for the solid cylinder as well, but assuming that A equal to 0 for the solid cylinder, right? So this is the same question, right? The question is, a solid cylindrical wire of radius r carries the current I, right? The ratio of the magnetic fields at points which are located at r by 2 and 3r distance away from the axis, right? So it means that we can just draw the cylinder here, right? We can just draw the cylinder. The cylinder is not a hollow cylinder. Cylinder is a solid cylinder, right? It means that it's fully filled cylinder, right? There is no cavity inside the cylinder. It's a fully filled cylinder. So the radius of the cylinder is given as capital R is the radius of the cylinder, right? Now we have two regions where we have to find the magnetic field due to this cylinder. One region will be R less than capital R, and another region will be R greater than capital R, right? So these are 2 points. One is inside the cylinder, and another point is outside the cylinder. And we know that outside the cylinder, the B outside for a cylinder will be nothing. It will be mu naught I upon 2 pi r, right? It will be 2 pi r. So this is the magnetic field due to this cylinder uh, outside region, right? In the outside region. But inside this region, we just calculated the magnetic field due to this what we call as hollow cylinder, right? We can write this equation here. B is equal to mu naught I upon 2 pi r times b square multiplied by r square minus a square, right? Multiplied by r square minus a square, right? Now for solid cylinder, this a will be equal to 0, right? This a will be equal to 0. We can just put the value of a here equal to 0. We'll be left with mu naught I upon 2 pi r, right? Into r square. And this b will be the capital R. B will be equal to capital R, right? And this will be capital R square. So this R and this R will get cancelled. We'll be left with mu naught I upon it's actually 2 pi r square, right? 2 pi r square and multiplied by this r, right? So this is for inside region. This is B inside, right? We can write it as B inside. Now we have to calculate the ratio of magnetic fields at a point which are located at r by 2, right? At r by 2, right? And 3r distance away from the axis, right? From the axis, right? So for outside region at a distance r equal to 3r, the magnetic field for r equal to 3r, magnetic field will be B naught. For B outside, that will be mu naught I upon 2 pi into 3r, right? 2 pi into 3r. And similarly for inside region, magnetic field at a distance of r by 2 will be mu naught I. The value of r is r by 2, so it will be r upon 2 upon 2 pi r square, right? This r and r will get cancelled. We'll be left with mu naught I upon 4 pi r, right? Mu naught I upon 4 pi r, right? We have to calculate the ratio. So the ratio B outside upon B inside upon B outside, right? B inside upon B outside. We have to calculate, right? So B inside is actually mu naught I upon 4 pi r, right? Divided by mu naught I upon 6 pi r, right? 6 pi r. So this and this will get cancelled, right? We'll be left with 6 upon 4, right? 6 upon 4. That will be equal to 3 upon 2. So 3 upon 2 is the ratio between these two magnetic fields. That means that the ratio of magnetic field inside and the magnetic field outside will be 3 by 2. So 3 by 2 will be the correct answer. This is another similar question. A hollow cylinder wire carries a current 5 ampere having inner and outer radius r and 2r. Magnetic field at a point which is actually 3r by 2 distance away from its axis. So we'll be using the same equation, right? That we use for the cylinder, right? For the hollow cylinder. This is the equation that we'll be using, right? So it will be magnetic field is actually equal to P is equal to I, right? I times mu naught multiplied with the factor R square minus A square, right? Upon 2 pi R B square, right? 2 pi R B square, where A is the inner radius and B is the outer radius, right? Now it's given in this situation that the current I is equal to 5 amperes, right? 5 amperes of current is flowing through it, right? Current I is equal to 5 amperes. Outer radius R and 2R respectively. Inner radius is R and outer radius is 2R, right? It means that our A is actually equal to R and B is actually equal to 2R, right? 2R. We have to find the magnetic field at a distance. R is equal to 3R by 2, right? R is equal to 3R by 2. So B will be equal to current is 5 amperes. We'll write here 5 times mu naught, right? And R is 3R by 2. It will be 9R square upon 4 minus R square upon 2 pi times R. R is 3R upon 2, right? Multiplied by B square. That will be 4R square, right? 4R square. This 2 and 2 will get cancelled. So we'll be left with, so it will be 5R square upon 4, or we can write it as 25 mu naught R square upon 4, right? Divided by, we'll be left with, it's 4 pi, 12 pi R cube, right? 12 pi R cube. 12 pi R cube. So P will be equal to 25 mu naught R square upon 4 into 12 pi R cube, right? So this R square and cube will get cancelled, right? So it will be actually 25 upon 24 times mu naught upon pi into R. So this will be the final magnetic field at this point, which is at a distance of 3R upon 2, right? For this hollow cylindrical wire. For this hollow cylindrical wire. So this is the net magnetic field. Now let's try to calculate the magnetic field due to solenoid, right? So we know that in case of solenoid, the total magnetic field is along the direction, right, along this axis, right? If this is how the wire is wound on this cylinder, right, in this fashion, and this is how the current is flowing through this wire, right? This is the direction of the current, right? The direction of the current can be either clockwise or anti-clockwise. Depending upon that, the direction of the magnetic field will be either towards the positive x-axis or it will be towards the negative x-axis, right? So you can see here, if this is the sense of the current on this in this solenoid, then the magnetic field using the right hand thumb rule, the net magnetic field will be along this axis, right? Along this axis, and here at this point, the magnetic field will be into the outside to the plane of the paper, right? And at this point, at these points, the magnetic field will be actually into the plane of this paper and perpendicular to the plane of this paper, right? So we have to calculate the magnetic field due to this infinite solenoid, right? and the total magnetic field is along the axis of this solenoid, and it is a uniform magnetic field, right? Straight represented by the straight lines. So we'll try to find out the magnetic field due to this solenoid along its axis, right? It's a infinite solenoid. So we'll be applying the Ampere circuital law. So you can see that this is the Amperian loop in this picture, right? PSRQ is the Amperian loop, and the length of this loop here is, let's suppose this length is A and this length is B here, right? This length is A and this length is B here, right? And we know outside the region of this solid infinite solenoid, the magnetic field is negligible, right? It's a negligible magnetic field, right? And the total magnetic field, which is uniform inside this region, and it's parallel to its axis, right? So we'll be using the Ampere circuital law. Will apply the Ampere circuital law over this loop. That's PSRQ, right? PSRQ. So applying Ampere circuital law, applying Ampere circuital law on loop PSRQ, right? PSRQ. PSRQ, right? You know that outside region, there is no magnetic field. It means that there will be no contribution to the net, or we can say that since the magnetic field in outside region is negligible, so the line integral from P to S will be actually equal to 0, right? It will be actually equal to 0. So we can actually write it as integral of P dot dl, right? It's a closed line integral, or we can open this integral like this. It will be integral of P dot dl, right? P dot dl from P to S, right? Then integral of P dot dl from S to R, and integral of P dot dl from R to Q, and finally integral of P dot dl from Q to P. So we have opened this closed integral into four line integrals, right? And we know that here the B magnetic field is actually B equal to 0, right? B is equal to 0. If B is equal to 0, it means that this integral will vanish here, right? This integral will vanish. So it will be equal to 0, right? Similarly, you can see that this PQ line, PQ line and SR line, right? PQ line and SR line. This is the direction of the magnetic field, and this line is perpendicular to the direction of the magnetic field. So their dot product with the dot product of magnetic field with these two lines will be equal to 0, because the angle between magnetic field and these two lines is actually 90 degrees. So the dot product between them will be equal to 0. It means that this integral will also vanish. So this integral will also vanish, right? So we'll be left with only one integral, that will be v dot dl from q to r, right? So we'll be left with only one integral, that's p dot dl from q to r, right? Q to r. And p is the magnetic field, right? P is the magnetic field. And let's suppose q to r is the length of a, right? Then integral of dl will be equal to a, right? So it will be equal to b into a. So this total closed integral has come equal to b into a, right? Now let's suppose this is an infinite solenoid, right? So we'll define a number of turns per unit length here for this case, right? So let's suppose n is the number of turns for this solenoid per unit length. Number of turns per unit length, per unit length. And let's suppose n turns are there, n turns are there, n turns are there between q to r, between q to r, right? Between q to r, and that will be equal to, actually equal to, n is the number of turns per unit length. So n will be the total number of turns between q to r. So it will be n into a, n into a, right? N into a, and this will be this b into a will be actually equal to mu naught I enclosed, right? Mu naught I enclosed. That's the Ampere circuital law. So b into a comes out to be equal to mu naught I enclosed, right? Right. So n is the total number of turns. For n number of turns, so B into A will be equal to n times mu naught I enclosed, right? Mu naught I enclosed. So n will be equal to n into A. We'll replace it with n A mu naught I enclosed, right? So I enclosed is I. Now this A and A will get cancelled. We'll be left with magnetic field B equal to n times mu naught I, right? N times mu naught I. So this is the magnetic field, total magnetic field along the axis of this solenoid, infinite solenoid. That's equal to n times mu naught I, right? N times mu naught I, where I is the current, n is the number of turns per unit length, and mu naught is the permeability of this medium, right? Now let's have a small discussion over the magnetic force on moving charge as well, right? You can see in this diagram, right? We have a charge here, the charge Q, and this charge Q is moving in the presence of an external magnetic field B with some velocity V. This velocity vector V makes an angle of theta with magnetic field B, right, in this picture. So the magnetic force, or we call it as Lorentz force, right? Lorentz force. The Lorentz force or the magnetic force because of the external magnetic field is given by this equation, that's Q times V cross B, right? It's Q times V cross B. It's the cross product between the velocity vector and the magnetic field vector, right? So this is the total net force acting on this charge Q because of the presence of external magnetic field, right? So Lorentz force or the magnetic force on moving charge is given by Q times cross product of velocity vector and the magnetic field vector P, right? Now the question is how can we find the direction of this magnetic force? So direction of this magnetic force will be given by the direction of this vector V cross B, right? So V cross B vector will actually give the direction of magnetic force on this charge, right? Magnetic force on this charge, right? Or we can find this using the right hand rule as well, right hand rule. So let's suppose we are placing our thumb in the direction of velocity vector, right? And we point our fingers along the direction of the magnetic field, then the direction of the palm will give us the direction of the force acting on the charged particle, right? You can see in this picture, we have placed our thumb along the direction of the velocity, and B is along the fingers are along the direction of the magnetic field, and the direction of this palm actually gives the direction of the magnetic force acting on it, right? So this is how we can find the direction using the right hand rule, right? But we can also find it's very easy to find the direction using the cross product between velocity vector and the magnetic field vector, right? So now let's discuss different cases here. There are many cases. We'll discuss each and every case one by one, right? Let's suppose that initially the charge was there was some the charge was at rest, right? The charge was at rest, and there is some uniform magnetic field lines like this. This is a uniform magnetic field P in this region. The charge is at rest. It means that whenever charge is at rest, then velocity will be zero. There will be no magnetic force acting on the charge, right? So charge at rest, it means if V is equal to zero, then F will also be equal to zero. Magnetic force will also be equal to zero. It means the charge at rest do not experience any magnetic force due to presence of magnetic field, right? Similarly, if velocity vector and the magnetic field vector are at an angle of 90 degree to each other, right? They are at an angle of 90 degree to each other. Let's suppose this is the velocity vector and this is the magnetic field vector here, right? And the angle between these two vectors is 90 degree. It means that the magnetic force will be equal to Q times V cross B, right? Q times V cross B. or we can write its magnitude as QVB sine theta, right? QVB sine theta, QVB sine theta. And the angle between the B and V vector is 90 degree. It means that in this situation, there will be a maximum magnetic force acting on this charged particle, right? So it will be equal to QVB. So it means that the maximum magnetic force will be maximum on a charged particle only when the angle between the magnetic field and the velocity vector is 90 degree, right? Then the magnetic force will be maximum, right? It will experience a maximum magnetic force, right? And similarly, if the charge particle is moving, if the charge particle is moving along the direction of the magnetic field, right? So this is the velocity vector, right? And this is the magnetic field vector, right? If this is the velocity vector and magnetic field vector as well, then the angle between them will be equal to 0 degree, right? Then the magnetic force in that case will be equal to sine zero, that will be equal to 0, right? So the net magnetic force in that case also will be equal to 0 degree, right? Similarly, if the charged particle and the magnetic force are anti-parallel to each other, in that case also the magnetic force on the charged particle will be 0, right? There will be no magnetic force in three situations. One, the charge is at rest. The second situation, when the angle between the magnetic field and the velocity vector is 0, or magnetic field vector and the velocity vector are parallel to each other, there will be no magnetic force, right? And similarly, when velocity vector and magnetic field vectors are anti-parallel to each other, then in that case also there will be no magnetic force on the charged particle, right? So let's try to solve a simple question here. A test charge 1.6 into 10 to the power minus 19 coulomb, right, is moving with velocity this uh, with velocity 2 I cap plus 3 j cap meter per second, and the magnetic field is along 2 I cap plus 3 j cap, right? The magnetic force on the test charge is, right? So we can find the magnetic force simply by using this Lorentz equation. That's Q times V cross B, right? Q times V cross B. The value of Q is given as 1.6 into 10 to the power minus 19 coulombs, right? And the velocity vector is actually given as 2 I cap plus 3 j cap, right? And the magnetic field vector is given as 2 I cap plus 3 j cap, right? 2 I cap plus 3 j cap. 2 I cap plus 3 j cap. So it means that the velocity vector and the magnetic field vector are actually along the same direction, right? So whatever the direction of velocity vector is there, same is the direction of the magnetic field vector, right? You can see that both these vectors are actually by magnitude and direction same, right? That means that there will be actually no magnetic force acting on this charged particle, or we can say that the force acting on this charged particle will be equal to 0. There will be no force on it because the angle between the velocity vector and the magnetic field vector is 0 in this case, right? So we can say that V cross B will be 0, right? The cross product here for this case will be equal to 0. So V cross B here is actually equal to 0. That's the reason the net force on this charged particle is equal to 0, right? Now, an electron is moving along a plus x direction. To get it moving along an anti-clockwise circular path in xy plane, magnetic field applied should be applied along, right? An electron is moving along a plus x direction, right? And we know that the direction of the magnetic force depends upon the sign of charge as well, right? If we have positive charge, this is the magnetic force because of the positive magnetic force on the positive charge, right? That's given by V cross B, right? V cross B, right? V cross B. But if the charge is negative, right? If the charge is negative, then the magnetic force experienced by the negative charge will be opposite in the direction to that of the force experienced by the positive charge, right? So, or we can say that we can get the direction of the magnetic force in a negative charge by B cross V, right? B cross V. If we do the cross product between B vector and the velocity vector, we'll get the direction of the force on negative charge, right? And we know that one more important property of that what we call as cross product is that V cross B, right, can be written as minus B cross V, right? Minus B cross V vector, right? So it means that it's B cross V vector, which will give us the direction of magnetic force on a negative charge, right? On a negative charge. And V cross B, with the help of V cross B, we can calculate the direction of the magnetic force because of the positive charge, right? So that's how we'll try to find the direction of the magnetic forces due to positive and negative charge. But in this question, the question says that an electron is moving along plus x direction. To get it moving along an anti-clockwise circular path in xy plane, right? Let's draw the xy plane here, right? The xy plane. This is xy plane, right? To get it moving along an anti-clockwise direction, right? In xy plane. So it means that this is the circular path in xy plane, right? Xy plane. So it means that if this is moving in an anti-clockwise direction, right? In a circular path, in xy plane, right, then the force acting on this particle on this charge must be along the direction of the negative direction of this y-axis, right? It must be along negative direction of this y-axis, right? So it will be along negative y-axis. So the direction of the velocity of this charged particle is this, right? It will be tangential to this circle, right? Tangential to the circle. Now we want to get the direction of magnetic field, magnetic force in the downward direction, right? We want to get the direction of the magnetic force in the downward direction. So this is the direction of the magnetic force, and this is the direction of the velocity, right? This is the direction of the velocity, right? So if we want to get the direction of the magnetic force in the downward direction, right? In the downward direction, it means that our velocity vector should be, this is the tangential velocity vector here, right? This is the tangential velocity vector. Let's suppose this is the direction of the magnetic field, right? If this is the direction of the magnetic field, then the direction of the magnetic force will be into the plane of this paper, right? It will be into the plane of this paper, right? It will be into the plane of this paper. So let's draw the direction of this magnetic field vector perpendicular to the plane of this paper and into the plane of this paper. Or we can say that if the direction of velocity is along minus vi cap, right? Minus vi cap is the direction of the velocity vector, right? Then force is along minus f j cap, right? It's along minus j cap. Then the magnetic field should be along the direction of minus k cap, right? Minus k cap. It means it should be into the plane of this paper, right? Into the plane of this paper and perpendicular to the plane of paper. Or we can say we can present the direction of the magnetic field by this cross symbol, right? So this will be the direction of the magnetic field. If we apply the direction magnetic field into the plane of this paper and perpendicular to the paper, right? Then the electron is going to show the circular path, move along a circular path, right? But the circular path will not be a clockwise, it will be a anti-clockwise circular path in this xy plane, right? So this is how we can find the direction of the magnetic field, because we have to get the direction of the force along the negative y direction, right? In order to get the force along negative y direction, we have to apply the magnetic field perpendicular to the plane of this paper, right? And into the plane of this paper. So represented by this cross symbol, right? So this is how we can apply the magnetic field. So we'll stop here. In the next lecture, we'll discuss we'll discuss the problems based on the previous topics as well. And we'll be discussing the different paths followed by the charged particle in presence of external fields, right? We'll be discussing the different trajectories of the charged particle in presence of external fields. Let's stop here. We'll meet in the next lecture. Take care and goodbye.